Much like many of the things that we learn in Physics 20, they start off pretty basic. But you want to be wary of that. You don't want to be lured into a false sense of security because things can get complicated quickly. So today what we're doing is we're setting the groundwork for more complicated things. I've called this lesson the language of motion. So we have to go through some definitions. And the reason is, there's a couple of reasons. If you don't understand the meaning of words, then we can't communicate effectively among each other. Okay? And if you get a job working at Jet Propulsion Laboratory, NASA's Jet Propulsion Laboratory, and you're not using the same language as the people around you, well, then there's a problem, right? Then you have accidents. Then the Mars rover doesn't land safely because somebody forgot to convert liters of fuel to gallons of fuel, which happened a number of years ago. They had a conversion problem. So that's one of the reasons why we look at using a common language. The other reason, and this is hard for you to appreciate right now, but every time it comes up, I'll point it out to you, is it turns out that the language you use translates into how formulas are used. And if you treat a quantity as, say, a scalar, and it's really what's called a vector, then when you do the work in the formulas to make your predictions about the future event, you will get inaccurate results. Okay? The toxicity level is going to be too high in the probe, or the probe's going to crash. I mean, these are important issues that you have to make sure you're getting proper results for. So the language is all going to be used to get proper results, to calculate things the right way, not the wrong way. So we're going to be looking today at kinematics, defining kinematics. Position, distance, and displacement. One other comment here before we get into this. You learn many of these things in Science 10, but the level with which you're expected to apply them and understand their meanings in Physics 20 is a lot higher. Okay? Define scalar and vector and provide examples of each, and then we're going to be doing some very basic calculations today. How many of you recognize all 6 of those bold words? Okay, you should, because you learned about them. And again, we're going to learn in more detail what they mean. So first of all, kinematics is a branch of physics that describes the motion of objects. Kinematics doesn't care about why objects move the way they do. Kinematics cares, and this is on page 1 of your unit handout, kinematics cares about using, I'll say, formulas or using rules of kinematics to accurately predict what's going to happen. So again, in order to successfully describe motion, you need to use the same terminology. So to begin with, a scalar is a measurement in science or physics that has a magnitude. Now, people get confused by the word magnitude. Magnitude can be thought of as amount. It's the numerical part of the measurement. It's the size of the measurement. But a scalar has no direction. A vector, on the other hand, is something that has a direction, but it also has a magnitude. So it has a number, but it also has a direction associated with it. So as an illustration here, if you were, I don't know, making a cheesecake, and it said that you need to add 75 milliliters of Cointreau, which I believe is an orange-flavored liqueur. That's a volume. And there's no direction associated with it. It isn't even that you could have a direction. It's that a direction would make no sense. Let's say I'm mixing some herbicide in a sprayer in my garage, and I need to measure out 75 milliliters of that substance, that concentrated substance, and I'm going to dilute it. I mean, imagine my surprise if I looked on the label and it said 75 milliliters east. What would that even tell me I'm supposed to do? I think I'd just go inside and have a nap because I would think I'm not thinking clearly. It makes no sense to have a direction. This is a magnitude. It's a size. If I say that the temperature of the kiln or oven is 120 degrees Celsius, 120 degrees Celsius upwards, towards the floor, north, it doesn't make any sense. Temperature is an example of something that has only a scalar. A large Mastiff dog has a mass of 45 kilograms, which is a little over 100 pounds probably, or close to 100 pounds. There's no direction associated with that, okay? However, and it's at this point, I know it was for me when I learned about physics and vectors, I wondered what the big deal is of including a direction. Well, we'll come back to that. But if I say to you that there's 120 newtons of force and it's east, this is considered a vector. There is a magnitude and there is a direction. And the simplest reason I can give you why force, that's what this is a vector, which means the reason I can give you that direction is important is whenever you use force, you use it to accomplish things. So if I want to move an object in a particular direction and apply a force to it, I want a certain outcome, I have to apply a force in a particular direction, right? If I want to design a rocket that's going to lift off from the surface of the Earth, and I design a thrust force, or calculate a thrust force, that force is going to be up. It's important that it's up. You're not going to design the engine so it applies a force to the right. It's more nuanced and complicated than that, but that's the point. There's something called electric field strength. An electric field strength has a direction. It has to do with the direction that electrons are going to be pulled in an indirect way. So if I tell you the electric field strength is 20 volts per meter upward, what that means is that there's some electrical action that's in the upward direction, and it has something to do with volts and meters. You're all familiar with the concept of lightning. In order to get lightning to occur, you need an electric field strength of around, I think it's about 30 million volts per meter, which means if you had a voltmeter, you may know what a voltmeter is. If you had a voltmeter and you take the two ends of the voltmeter and you put them in the air 1 meter away from each other, and the voltmeter reads 30 million volts, then you better get out of the way, because lightning's about to happen, if it hasn't happened already. By the way, you would never put one hand and another hand across a voltage of 30 million volts. You'd just be a pile of cinder and dust. There'd be nothing left, okay? So again, there is a magnitude and there's a direction. Does this idea ring a bell from Science 10? Okay. So, and here I'm going to get into kind of, if you look on the front cover of your unit handout, kind of the importance of scalars and vectors. And you will not appreciate this fully, but you will appreciate it on some level. These are what I call the 5 kinematics equations or formulas. And it's quite intimidating when you look at them. And it turns out that any of these things with arrows over top of them are vectors. And if you don't include the direction in your calculation in this formula, you don't get the right answer. Okay? So much of what we do is going to rely on you understanding that vectors can be put into formulas, and in some way you can put the direction in the formula. So what is position? Position is where an object is at a specific point in time. It is probably the most useless thing we can talk about in this unit. Because we don't talk in physics about where objects are. We're more interested in how their motion changes. We're more interested in maybe where they are compared to where they started, and that's different. So position tells you where an object is, and it needs to be described relative to some point. So if I say to you, what is the position, where am I right now? What's my position? You can't just say here. You have to say in room 127. And then all of a sudden you're into this reference system where room 127 of what? Oh, room 127 of Wetaskiwin Composite High School in Wetaskiwin. We have this problem of having to define where we are compared to elsewhere. So if you said that the bakery is in Millet, and nobody knows where Millet is, then you have to say, oh, the bakery is 13 kilometers north of Wetaskiwin. But maybe you don't know where Wetaskiwin is. So position has problems associated with it. We'll come back to that in a bit. There's got to be some reference point that we use. Distance is pretty obvious. It's how far an object has traveled during a time interval. And displacement is where an object is at the end of a time interval relative to where it was at the beginning. This is the most useful thing. Listen, if you're running, if you're doing a race, you're probably interested in distance, how far you run. But very often in physics, we care about the displacement. We care about the overall change. Where's this thing now compared to the very beginning? We don't care about what happens in between. We don't care about how it got to that final position. Speaking of position, if displacement is where an object is at the end compared to where it started, then it's really the change in the position. And we're going to do a couple of examples to illustrate this. So these are the definitions for position, distance, and displacement. That's the focus in this lesson. That's what this lesson is about, those three things. So I want to talk about the word change, because I said over here that displacement is the change in position. And this is not in your notes, but you need to know it. So whether you write it down or you just mentally make an image in your head of it, that's fine. You've seen this triangle before, and it means delta. It's read as delta because it's a Greek letter. It happens to be the capital Greek letter delta. It's like our D, okay, kind of. And we use that almost exclusively in math and science to mean the change in a quantity. What does that mean? Well, let's say I said to you that you're at the base of Mount Everest or some station below the summit, and the current temperature is 3 degrees Celsius, and it can be quite warm at the base of Mount Everest. And on the summit, it's 17 degrees Celsius. And I say to you, what is delta temperature, delta T, from the base to the summit? I'm asking you for the change in the temperature. Temperature, by the way, is a scalar. And I want everybody to think about this for a second and see if you can come up with an answer to this question. When you go from 3 degrees Celsius, positive 3, to negative 17, what is the change in temperature that you experience? So I'll give you a minute to think about that. Is there anybody who wants to stick their neck out and give me an answer? Nobody? You're hesitant, and I get that because there's obviously a wrinkle to this question. There's an answer that many people will say that's wrong. So now that I've really boosted your confidence, is anybody willing to give me an answer? Yeah. 20. It's not 20 degrees Celsius. It's negative 20. And you see, so you put 20 into a formula, you're going to get an incorrect result. You put negative 20 and you're going to get the proper result. So the details here are important. By the way, I'm not suggesting that temperature is a scalar. I'm suggesting that the change in temperature can be positive or negative. If you go from positive 3 to negative 17, I hope you agree it's gotten colder. So if somebody said to you, oh, what was the change in temperature from Edmonton to Miami? And it was really positive 40 degrees Celsius, and you said negative 40, that's wrong. So whether it's positive or negative is important. And here's how you get the right answer always with delta. Delta is always the final minus the initial. Always. Now, you'll get to physics 30, and there's one exception to that we want to avoid that. So if I were to take the final temperature of negative 17 degrees Celsius and subtract the initial temperature of positive 3 degrees Celsius, I'm going to get negative 20 degrees Celsius. And I hope you would agree, since this is a change, since this is a change in temperature, the negative is significant. It's telling you it got 20 degrees colder as you went from the base to the summit. You know, a different example that I could use is maybe at the beginning of the month on, we'll just go January 1st. Beginning of the year on January 1st, I have an investment fund that has $10,100 in it. And it's a fluctuating fund. It's not guaranteed interest. My bank invests the money in different markets, and if it goes up, and I get money, and if it goes down, I lose money. And if on January or December 31st, at the end of the year, I have that much money, what do I have? Other than really sinking feeling, what I have is a loss of $4,000. So if you said, well, what's your delta investment? What's your change in investment? And I went, oh, it's $4,000. It isn't. It's negative 4, because you take the final, which is later, minus the initial. So I think that's very important, because when we go back to this definition for displacement that I've got at the bottom of the screen here, we're going to be using that idea from time to time, and we have to subtract in the proper order. Otherwise, you will not get the right result. All right, let's talk a bit about speed and velocity. Speed is how fast an object is traveling, obviously, and velocity is how fast. And it may seem to you, what's the big deal? But it's how fast and in what direction. Once again, I don't mean to imply to you that if you take a speed and you just throw direction on it, you get velocity. There's more subtleties to that. But once again, everybody, if you don't understand the difference between these two ideas, then when you do calculations, which is what a big part of physics is, you will not get the right answers. Okay? This is the focus in later lessons. So today we're focusing our energy and attention on position, displacement, and distance. So, question. Some of these terms are scalars and some are vectors. Provide an example of what each measurement might look like and label it as a scalar and a vector. Well, I think we've already established that something like temperature is a scalar. By the way, this is a mistake. It's not, no. It is a mistake that's in your Science 10 textbook from time to time. They seem to imply really strongly that if something can be negative, it's a vector. No. Temperature can be negative. That doesn't make it a vector. The negative isn't a direction. If I say the temperature outside is negative 10 degrees Celsius, imagine I said it's negative 10 degrees Celsius east. You'd look at me and wonder if I'm okay, because there's no direction associated with temperature. So it's a scalar. So a temperature might be, well, let's use negative 10 degrees Celsius. And by the way, that's the magnitude of the temperature in my example. Speed is simply how fast. So this is a scalar. I don't know. 32 meters per second. Could be anything you want. Distance is a scalar. It's just how far. See, if I tell you, I don't know what it is in kilometers, a typical marathon is 26 miles. I don't know how many kilometers that is, 42 maybe? Doesn't matter. If you tell me, well, you ran a marathon, and I didn't know how big a marathon was or anything about it, and I said, well, how far is that? What'd you run? You say 26 miles. I have no idea where you were. I have no idea where you started. I have no idea where you finished. I have no information at all. There's no direction associated, so I can't locate it. Whereas when you take a look at the other three have to be vectors. If you say your position is 10 meters, I have questions for you then. 10 meters where? 10 meters to the left of a doorway? 10 meters above the surface of the earth? So position, I'll say 10 meters left of I'm going to have to say a reference point here. This makes it a vector. And I'm using to the left for a reason. Sometimes science is tricky. If I say that the position of an object is 10 meters to the left of some reference point, and we'll have an example in a few minutes that talks about a reference point, instead of saying all of that, what I could say is that. I could say the position is negative 10 meters. As long as we all know where the reference point is, then we know the position. Okay? And the reason why I'm choosing that example is I want you to contrast this position of negative 10 meters with this temperature of negative 10 degrees Celsius. The negative in this 10 meters is telling you a direction. Left is negative. The negative in the negative 10 degrees Celsius is not telling you a direction. So negatives can mean directions, which means they can be associated with vectors, but just because something is negative doesn't mean that's the case. Displacement. Well, displacement is definitely a vector. And maybe an example of a displacement is positive 40 meters, or 40 meters right. Now I'm leading up to something here. And although I said this is pretty basic stuff, it's slippery. You think you have it sometimes, then it'll slip out of your grasp intellectually. The positive means to the right. I have a question for you. And this is all about the difference between position and displacement, because they're easily confused. See, with my example of position, I said that this negative 10 meters means 10 meters to the left of a reference point. Okay? Why is this not 40 meters to the right of a reference point? Why do I not say right of a reference point? Does anybody know? Go back. Yeah, Maxime?
Because it's 40 meters from the position, from the starting point.
Right. The difference between displacement and position is where it is at a point in time. Displacement, if you read the definition of displacement, it's where an object is compared to where it started. So, in some ways, the position is very informative. It tells you where an object is. Because all this is telling me is, I don't know where it is, I don't know where it started, I don't know where it finished, but I know it finished 40 meters to the right of where it started. That's what it means. Okay? And it's this displacement is the thing we're going to use most often. Velocity obviously is a vector. And we're not going to get into any real details here today. Let's go 100 miles per hour. Up. Directions are very often put in square brackets. By the way, if I had 100 miles per hour up, I could write positive 100. But traditionally, we kind of use up as positive and down as negative, and you'll get lots of exposure to this, and left as negative and right as positive. So if we have an object that's moving left, right, positive is in this direction to your right, negative is to the left. Any questions with any of that? All right. Panda, the puppy, is sitting 3 meters to the left of her chew toy. What does she do? She walks from that starting position, it's a position, a total of 8 meters past the chew toy. So she's actually walking more than 8 meters. If you use the location of the chew toy as a reference point, what is Panda's initial position? Okay, so that's Panda. That's my dog. Well, was my dog. She starts at the chew toy. If you look at your diagram that I've given you, there's a dot on the chew toy's position. So what that means is if we're using that as a reference point, that's 0. Okay? I'm sorry, I think I said she starts there. She doesn't start there. She starts to the left. But that's the reference point. So if I said to you, what's her initial position? She starts here. This is her initial position. How can we describe that? Well, what we can do is simply say the initial position is -3 meters. Because she is 3 meters to the left of the reference point. Now, I want to maybe just jump ahead here a little bit. So, you don't need to worry about writing anything else, but if I were to jump ahead to example 2, and you don't have to. There's example 1 right there on the screen. If you look at example 2, what if we use this point as the reference point? That's what example 2 is saying. Well, what that means is that Panda's initial position under these circumstances is 0, isn't it? So I want you to notice that we get different answers, which is a very useless thing in science. They're both correct. But, when you try to communicate with people about physical problems in the world, you want to use the same reference point. And this is kind of an arbitrary situation. What's the reference point? Well, I don't know, let's choose the chew toy. No, let's choose Panda's initial position. It becomes clunky. Okay. So let's get back now to example 1, where we said that this is her initial position. And we'll come back to this idea that it's going to change. The number will change if we change the reference point. What's her final position? Okay, so what does she do? She walks so that she lands 8 meters to the right of the chew toy. So she goes over here, loses her attention of what she was after, gives herself a little bit of a scratch, and then she walks 2 meters closer to the chew toy. So she starts here, I for initial. She finishes here, F for final. You with me on that? So where does she end up? She ends up with a final position of +6 meters. She ends up 6 meters to the right of the reference point. I'm not talking about how far she's traveled. I'm not talking about any of that. I'm talking about always comparing her position to this position. So the difference between 8 and 2 is 6. This, I'm sure you've clued into how I'm getting 6. That's where the 6 meters is coming from. And she is to the right of the chew toy, which is the reference point. Okay, so how far has she traveled? We don't need to use complicated physics or definitions here. How far does she walk? Well, she has to walk a total of 3 meters plus that 8 meters plus that 2 meters, right? She walks from here to here, which is 3. She walks an additional 8. She stops. She walks an additional 2 meters. So by my count, I'm getting 13 meters. Okay. Now, what's her total displacement? The word total is used because we can use the idea of adding things, and I'll show you that in a second. But displacement is where an object ends up compared to where it started. So if we clear the slate here, this is where she starts, this is where she finishes. That's the bottom line. It doesn't matter what happens in between. So it doesn't matter what the reference point is. There's an answer to this question regardless of the reference point. And the answer is going to be 9 meters to the right. How's my thinking there? That this is a total of 3 meters. This is a total of 6 meters from here to here. She ends up 9 meters to the right of where she started. So we can put 9 meters right, or +9 meters. If we all agree on the same system, which is to say that to the right is positive, then we're okay. Very simple example that's just getting you to think a little bit, but does anybody have any questions with this example? Okay, so now what happens if we change the reference point? Because a reference point is an arbitrary thing. Where is Mr. Way standing? 1 meter from that cabinet. 1 meter to the right of that cabinet. Where is Mr. Way standing? 7 meters to the left of that wall. They're both correct because you can choose anything for a reference point. So we choose this point as a reference point right here. So what's Panda's initial position? Well, that's where she starts, and that's called 0. What's her final position? Well, she ends up over here. Forget about what she does. We know she ends up over there. That's important. So where does that point lie relative to that position? It's, I guess, 9 meters to the right, positive 9 meters. Do you agree? Okay. When we talk about position, we probably don't want to use words like to the right. We want to put just positive 9. By the way, we will very rarely make use of positions in formulas. It's all about displacement. Okay. What's the distance she travels? Does changing where we call 0 change how far she traveled in her journey? No. It's still going to be, what was it, 13 meters? Okay. You could do this. You could. But that seems to imply to me that you think there's a direction associated with it, so I would avoid that. It's just she's walked 13 meters. So what's her total displacement? Well, her total displacement is where she ends up compares to where she started. Well, she started here and she ends up in that position, so that's a total displacement of positive 9 meters. Now, this is subtle. It turns out in this frame of reference, using this as a reference point, her displacement and her final position are the same only because her initial position was 0. Right? But I want you to notice that all this meandering back and forth, in terms of finding distance, that's important. But in terms of finding displacement, we did not need to look at that. Because total displacement means you add the displacements. So, what was her first displacement? Let's go back and read this question carefully. She walked from here to here. Would you agree that's a displacement of 11 meters to the right? Okay. So one of Panda's displacements was 11 meters right. And we're going to add to that her second displacement, which I believe was 2 meters left. Well, how do you add things with directions? I'm getting a little bit ahead of myself in the course, but the answer is you change the directions to mathematics. Right means positive 11. Left means negative 2. And that gives you 9. So, I want to, because we have time, this is not a race today, I want to give you a couple of different illustrations here. You don't need to write them down. If I tell you 2 quick examples on the fly, and we'll get to formal examples in a second, that you have a situation, it doesn't matter what we're talking about here. It could be a kitten or whatever. Bumblebee. That an object has an initial position at negative 20 meters and its final position is 24 meters, positive. And then I have a different situation where I have the following displacements. So I'm telling you, in the first case, no information about what the object did. I'm just giving you a snapshot of the beginning and a snapshot of the end. I'm saying where it starts and where it finishes. Second example, I'm not going to tell you where it starts and where it finishes, but I am going to tell you that it undergoes these 4 displacements. So we have objects moving. They're the same kind of problem. But in case A, you've got 0 information about how it's accomplished. You just know it starts here and it finishes there. And in case B, you don't know where this is happening, but you have all of the intimate details about what's going on. And I say to you, what is the displacement in each of these cases? Well, how do I find the displacement here? I remember that it's change in position. Right? Final position minus initial position. That's easy. All I have to do is take positive 24 and subtract negative 20. And I don't even want to think about what's going on here. I get 44. Positive, right? And I hope you would agree that if you look at a number line, my nose being 0, if something starts at negative 20 and ends at positive 24, it's moved to the right 44. But this rule takes the thinking out of it, which is not a bad thing. So this gives us 44 meters. Now, you could do the same kind of thing here. You would just have to come up with a reference point, but that makes it complicated. Instead, what you do is you say, that, because on a map, east is to the right, and to the right is positive. Am I wrong in saying it's 13? I'm not wrong? It's 13. Okay. Which means in case A, the object ended up 44 meters to the right of where it started, and in case B, it ended up 13 meters east of where it started. So when you find total displacement, sometimes you use this idea, sometimes you use that idea. Let's take a look at the next question. With that in mind, I'm going to give you a minute to calculate the displacement in this situation. We have a frozen turkey whose initial position is negative 10 meters and final position is negative 34 meters. What's the displacement? And explain what that means. So write down your answer. Because displacement is a vector. So again, it's more complicated than saying, oh, all we have to do is add a direction and it becomes a vector. There's more to it than that. But this is the symbol that we can use. The difficulty with this notation and where it gets sticky is there's no real symbol for position in physics, which actually is kind of nice because it tells you then we won't be using position. We can do this if you like. You can say that the displacement is the change. I'm just going to ask us to use the word position here. I don't want to use a letter for position. That removes the stickiness if I just say that. And that means that this is the final position. I'll do a bit of abbreviating here, minus the initial position. Remember, it's always final minus initial. That's all. So all we have to do is take the final, which is negative 34 meters, and subtract the initial, which is negative 10 meters, and get negative 44 meters. I believe that's right. Oh, nope, nope. My mistake. We have to subtract negative 10, which gives us negative 34 minus negative 10, which is negative 24 meters. Better? Okay. So what's the scenario? The turkey moved, not of its own volition because it's frozen, unless it's a zombie turkey. Somebody carried the turkey 24 meters to the left. That's what happened. So all I'm asking for is an interpretation of this. I'm not even going to go. I was going to say it lands 24 meters to the left of where it started. That's not what's important. It's moved 24 meters to the left. Mass on the end of a spring moves up 14 centimeters and down 6 centimeters. So in the previous example, everybody, we were given positions, right? So we could go final minus initial. Here, I don't know where this is happening, but I have some displacements. I want to find the total displacement. So I'm going to add the displacements. I'm going to take one of the displacements that I'm told, and I'm going to add the second displacement that I'm told. So if I say the mass on the end of a spring moves 14 centimeters up, then that's D1. That's one displacement that the mass on the spring undergoes. On the other hand, I say it then moves 6 centimeters down. So that's the other displacement. I'm embedding within the displacements positive for one direction and negative for the other. And going back to my point about the formulas on the cover page, that's what we're going to have to be careful of eventually. That anytime you see something with a vector symbol, you better ask yourself if the number you put in is positive or negative, because if you put in the wrong one, you'll get the wrong answer. And that works out to positive 8 centimeters. That's the displacement. Now, what's the total distance? Well, I'm going to add two distances. This D1 right here that I'm pointing at is different than this D1. I know you can quibble and say, well, aren't they the same? I'm going to say, no, they're different. The D1 on the left is positive 14 centimeters. The D1 on the right is 14 centimeters. It's neither positive nor negative in a weird kind of way. I know it's a positive number. It's neither positive or negative. It's just a magnitude. It's just a scalar. We don't want to elevate it to the importance of being a vector by saying plus 14. That would be a mistake. Plus, well, what is D2? D2 on the left, that's a vector. That's displacement number 2. This D2 is distance number 2, and it's just 6 centimeters. So the total distance is 20 centimeters. And this is maybe what I mean when I say you learn about this in Science 10, but we're going to dig down deeper here. We're going to start really, really digging down deep into what these things mean. Because everything we're doing here with these distances and displacements, we'll be able to do with forces and electric field strength in Physics 30. And acceleration and anything that can be considered or is a vector. Any questions with 4? All right. Number 5, in an alternating current in a wire. So when you plug something into an outlet, there's electricity that happens, and electricity is a flow of charge. the flow of electrons in things that you plug into a wall outlet is different than the flow of electrons in things like a flashlight battery. So when I connect a battery, this is the symbol we use for a battery, to a light bulb in a flashlight, and this is the symbol for a light bulb, what happens is the electrons move around and around and around through the circuit. If you take Chem 30, you'll learn that this is called an electrochemical cell, and the electrons are being pushed due to a chemical reaction that's happening. This is called direct current. Those electrons just keep going around until you run out of chemicals to drive them. When you take a look at plugging something in, like a toaster, that's a toaster, and you plug it in to an outlet, that's an outlet, what happens is all of the coils in there get hot because the electrons are flowing around, just like this coil would get hot. I know you don't see these types of light bulbs very often. They're almost always LED or something else, right? But you know what I'm talking about here. This would get hot because the electrons are losing energy as they flow through. The coils in the toaster get hot, but for a different reason. The electrons are flowing through, but rather than the electrons flowing downhill all the time, it's like somebody over here is taking the hill and doing this to it. And the electrons roll downhill and lose energy, and then they roll downhill and lose energy. In other words, the electrons in the toaster are shaken back and forth. If you really want to know what's happening, this is a negative and this is a positive. In an alternating current, that negative and positive keep switching. And we learn about how that happens in Physics 30. So it turns out that an electron will go back and forth a full oscillation in 1/60th of a second, which is a very tiny period of time. So these electrons are really dancing back and forth quite quickly. So, in a 1-second interval, how far does an electron travel? Well, it travels a distance of 1.2 times 10 to the negative 5 meters in one direction and 1.2 times 10 to the negative 5 meters in another direction in 1/60th of a second. Which means in a full second, this will be our distance. In a full second, if we multiply that distance by 60, we will get the total distance. How many of you have heard hertz, like 60 hertz, as a frequency? That's the frequency of alternating current in North America. It's different if you go overseas. Okay? Or I think South America might be different. So I include this example because I want to make sure you know how to properly use your calculator, okay? And don't scoff at this because some people don't know how to use this properly. When you enter scientific notation, is this the final example? Or is there one more? Okay. When you use scientific notation, do not do this. Do not go 1.2 times 10 raised to the negative 5. Ever, never, ever, ever, ever. Okay? Don't do that. What you do is you go 1.2 and you choose the EE, which for some weird reason stands for exponential notation, and only one E comes up. And then you enter negative 5. And this locks it together. The calculator knows you mean 1.2 times 10 to the negative 5. So we have to add that to itself. I'm just going to double it. So this is the distance that it travels in 1/60th of a second. And if I multiply that by 60, I get this. 0. Should have taken a closer look, but I think I have it. 0.00144 meters. About 0.1 of a millimeter. contrasted with the total displacement. Who can tell me who's already calculated the total displacement? Do you know? It's a calculation you can pretty much do in your head. The electron goes back and forth. It's going to be 0. If you want to do this clinically, like technically properly, then it would be this. Because, let's say it moves to the right 1.2 times 10 to the negative 5 meters, then it stops and it moves to the left. So to the right is positive, to the left is negative. That's going to be 0. If I start on a oval racing track and I run from that starting point 10 times around the track, my displacement is 0. I mean, assuming I end up in the same exact location that I started. So the fact that this is going back and forth means the displacement will be 0. We okay with that example? Okay. Pretty easy one. What is the total distance traveled by this person? They go 40 meters north, 80 meters south, 70 meters north. When I calculate the distance, the north and south has no bearing, no pun intended, on my answer. The total distance is going to be whatever 40 meters plus 80 meters plus 70 meters is. I'm adding distances, which is 150. I get 190 meters. Anybody want to verify my arithmetic there? Pretty sure that's right. When I talk about the displacement, I'm not going to tell you how to get the answer. But what some people will do is they'll draw this out on paper. They'll draw a line that goes 40 north, and then they'll go 80 south and 70 north, and they'll try to take a geometric approach to it. It's so much simpler to just say positive 40 plus negative 80 plus positive 70. Yeah, it'd be another 5 minutes or so.
I was like, I thought they left him on the door.
So we're translating a direction into a number, a positive or negative number. Does that make sense, you guys? Are you with me? Okay, so I don't know what that works out to. I think 30 just by glancing at it. So we get the displacement is positive 30 meters. And again, over here with the 190, I can't stop you from doing this, but if I see a student do that, I start to question whether they really understood what they found. Because there's no positiveness to this. Again, it's a positive number, but it doesn't mean anything. So we're good? You have a couple of sets of problems to work on here.